Hello, everyone. My name is Wenjie Huang, and I'm a PhD candidate from the Chinese University of Hong Kong. And the topic of my presentation is a quick method for evaluating the disinfection effectiveness of Far-UVC light on bioaerosol transport based on Markov chain model. Let's begin with the background. As we know that in recent years, the frequent outbreaks of airborne diseases have caused significant damage to human health. And for example, the most recently, the COVID-19 has already killed more than 6 million people around the world. And the influenza breaks out every year and caused many deaths. And for these pandemics, the airborne transmission is a major route, which is defined as a spread of aerosols. And these aerosols can be generated by human activities like coughing, sneezing, and even breathing. Due to the tiny size, these particles can remain suspended in the air and travel a long distance to infect others. So it's crucial to implement the effective strategies to control the spread of the infectious aerosols indoors. We know that as a control measures, the UVC light has been widely used in indoor environment for disinfection. But since it is harmful to human health, it's just used in the empty room. But very luckily, we have the Far-UVC light, which is safer for human use and eyes, so we can use it in the occupant rooms. That means that Far-UVC can be an effective way to control the person-to-person bioaerosol transport. In the applications, there exist many factors that will impact the disinfection effectiveness of the Far-UVC light. For example, like the different ventilation pattern or the different source characteristics and the different installation locations of the UVC lab. So in order to optimize the effectiveness of the UVC lab, we need an accurate and rapid method for the assessment and design and the different conditions. And for the method, the experiment and the numerical simulation are commonly used. The experiment can reflect the real situation, but it costs lots of time, workforce, and material resources. On the contrary, the numerical simulation can easily control the started condition with a high efficiency, and it can provide more detailed information. That means the numerical simulation is a effective method. So in this study, we aimed to develop a numerical method for quickly evaluating the disinfection effectiveness of Far-UVC light on indoor bioaerosol transport. And this model is a Markov chain-based UVC disinfection model. We first used the computational fluid dynamic to calculate the airflow distribution. And then in the Markov chain part, we use two probability metrics to represent the particle, the bioaerosol transmission indoors. We can say that first, the particle transport under the effect of airflow is considered using the transition probabilities. And then the disinfection effect of the UVC light is considered using the survival probabilities. And for the P matrix, it is based on the airflow. And we can see that in a computational domain, we separate this domain into several cells. And the transition probabilities means the probabilities of particles transport from one cell to another. And it can be calculated based on the airflow rate between the cells. And the particle number in a cell after a time step equals to the sum of the remaining particles in the cell and the incoming particles from the neighboring cells. And the next is the survival probabilities. In this part, these probabilities means the proportions of the bioaerosols still alive after time step. When the UVC light is off, it can be calculated based on the lateral decay coefficient. And when the UVC light is on, the disinfection effect needs to be added, and it can be calculated based on the susceptibility constant and the UV irradiance distribution. And in this part, the lateral decay and the stability constant can obtained from the experiment, and the distribution of the UV irradiance can be calculated using the view factor models in the previous study. And to validate this model, we conduct an experiment in a ventilated chamber. And we use two mannequins to simulate the occupants. And the Far-UVC light was installed on the ceiling with 3 different locations. The E. coli was released from the mouth of the mannequin behind, and the samples were collected in the breathing room of the mannequins in front. The experiment was taken for both UVC on and off. And this slide shows the result of the validation. And these 3 figures shows the transient bioaerosol concentration at 3 different, when the UVC light is installed at 3 different locations. And the curves are for the simulation, and the points are from the experiment. And we can see that for all of these 3 locations, and the predicted concentration agreed well with experimental data. That means the model can correctly predict the particle transport indoors. And for further comparison, we calculate the disinfection efficiency based on this concentration. And we can see that the proposed model can correctly predict the disinfection performance of UVC light. And this table shows the computing time. And we can say that if we use a traditional model, like the Lagrangian model, we need 14 hours to calculate the particle transport process. But with our proposed Markov chain model, it just takes about 400 seconds to compute this process. So it's very fast. In conclusion, this proposed Markov chain model shows an overwhelming superiority in computing speed and with a reasonable accuracy. And this model can be used for the faster design of the UVC lab installation locations to optimize the performance. That's about my presentation. And if you are interested in the detailed information, you can refer to our related papers. Thank you for your time and attention.
Questions? One up here and one over here.
So you said that the Lagrangian approach takes so much longer than your Markov chain approach. Do you have any kind of understanding of the work versus the accuracy for your method versus the Lagrangian method? Because I would assume they would both be kind of linear, but they might cross at some point based off of the accuracy you're targeting. Do you have an understanding about what the convergence is or anything like that?
For the proposed Markov chain model, there is no convergence because we don't lead the iteration. And for the Lagrangian model, because we need to track the trajectories of many particles, for example, millions of particles to get the statistically meaningful result. But for the Markov chain model, it's more like the Euler-Ring one. But since there are some assumptions that make it simple, that it will not need the iterations, so it can be quicker.
But you said to reasonable accuracy, what did you determine as reasonable accuracy?
Maybe I mean, it's agree well with the experimental data.
Okay, okay,
Thank you.
thank you.
All right, thank you so much.